We move now to our second speaker of the session. So we will continue on printed electronics. So the talk is titled "Printed Electronics from Lab to Industry," and it will be given by our colleague Kevin Rodrigues from Centi in Portugal. So Kevin, thank you so much for being part of the school, and the stage is yours whenever you're ready.
Thank you, Pedro. Can you hear me well?
Yeah, perfect. Loud and clear.
Perfect. So I will share my screen. I hope you can see it. Please let me know when you see it.
You can see it. Yeah,
it's working?
Yeah.
Perfect. So first of all, I would like to thank you for the nice invitation to attend this event and to share a little bit what Centi is doing in the field of print electronics and how we are helping the industries to implement these solutions in their products. First of all, I'll talk a little bit about Centi just to make a brief context of what we are and what we do. So we are a Center for Technology and Innovation located in Portugal, in the north part of Portugal, in the city of Famalicão. And basically, we focus on research, technological development, and engineering based on the development of nanotechnology, advanced materials, and smart systems for different and multiple applications. We are divided in different technical domains that go from functional materials up to design and engineering solutions. So our main goal is to support our industries with the development of novel solutions, novel materials that they can implement in their products and have solutions with high added value that they can bring to the market. We have a multidisciplinary team, so our technological focus is very, very broad. It can go from material-based solutions like nanostructure solutions up to microfabrication and printed intelligence, up to advanced energy storage and processing. So right now, Centi has a very, very big focus in the development of new solutions for the energy sector. And the beautiful part of print electronics is that they also can make a part of this area. And I will show you some examples of how printed electronics can be involved in this energy storage sector. And we also have our own smart system department completely focused on developing hardware, firmware, and software solutions to all the smart devices that are created within Centi. And of course, we are also based in some thematic principles and bioeconomy, sustainability, performance, digital transformation of material and processes are areas that we address throughout our different technical departments with our industrial partners to assure that not only we can have functionality, we can have technology, but at the same time, we also comply with their requirements and with the values that the company has. As I mentioned, we have a multi-sectoral approach. So our focus and our main know-how is based on materials and material technology, but we address and we adjust the characteristic of our solutions according to the different sectors' requirements, and we can work from automotive and aeronautics up to wearables, health, well-being, up to energy storage and generation solutions. Going directly to the topic of today, so print electronics. Something that is very important for me today to pass out is the wide application field that this area has, the different processes and technologies that might be involved with print electronics, and the high versatility and freedom that this type of process can exhibit. So basically, in terms of materials, we have a wide range of materials that can be applied for development of both functional and the decorative inks. Printed electronics, we also always think in flexible, lightweight, but in fact, it also is very versatile, and we can apply it, for example, also to rigid substrates. We have different examples where we have been working, for example, with ceramics, with concrete, where we also can apply these devices, and we don't add flexibility because the substrate itself is not flexible, but at the same time we have functionality to the structure. And in many cases, like for example, in scenarios of structural health monitoring, this is a very interesting technology that can be implemented in this type of scenarios. Nevertheless, it has many technical features that can go from flexibility, conductivity. The main appealing area of printed electronics is the fact that through roll-to-roll processes or layer by layer processes, we can have a low production cost and a scalable solution. And the high versatility also, but at the same time, complexity of printed electronics is the fact that we can combine different inks with different materials, with different functionality, build up multi-layer structures. Like, for example, electroluminescent lamps have up to 4 different conductive inks that can be applied. So we can have a really, really wide range of applications along the devices that can be created, and some of the applications that we have been working throughout the years. Centi has a long 15 years experience in the field of printed electronics. We have been working with different types of environmental sensors, smart packaging, flexible solar panels, medical devices, up to sensors to monitor battery conditions. So different areas can be explored. Today, I will focus in 2 main domains, namely smart textiles, how print electronics can bring value to smart textile-based solutions, and also in mold electronics, because along with some Portuguese companies, we have been working within this field and try to have new products in this area. How can we apply printed electronics? Here are some examples of technologies that we explore within Centi for the development of printed electronics. On one side, screen printing is one of the most versatile techniques. It can be applied for both flexible and rigid substrates. In this case, we have equipments both from roll to roll, but also in this case from sheet to sheet printing with high resolution and reproducibility. It has a wide versatility in terms of design, and it can be compatible with different inks and pastes, which makes screen printing one of the most used printing technologies in the field of printed electronics. Nonetheless, there are some emerging technologies that can bring added value to specific cases. For example, 3D printed electronics is a field that has been growing through time, and this is a technology that at Centi what we also have been developing for our partners. And basically, it's a process when we can apply our inks, our pastes, which need to have different viscosity conditions, but can be used through other techniques besides screen printing, like inkjet printing, nanojet printing, or dispensing. And this makes the possibility to print directly electric circuitries on 3D parts, which is highly interesting in some cases where we don't have many capabilities to apply a printed circuitry in a flexible substrate. So we need to address directly the 3D part itself. So it's a technique that in some specific cases can bring added value to the user. Now, in a later stage, roll-to-roll systems is the way to go, because if we want to apply and industrialize printed electronics, to achieve the low cost production that we intend, we need to have a pilot line that can take the most advantages of the inks that are applied and the substrate that is applied, and try to produce the lower cost possible devices. So in this case, we are also using this technique. We have a pilot scale production line that works in a roll to roll and allows us the deposition of different types of films and inks only in flexible substrates, as the technique itself exhibits. What are the main tendencies in terms of printed electronics? So through our expertise, we have been developing different solutions for our partners right now, and by our training domain, also in fairs like, for example, OPEC, etc. We have been noticing that these are the main growing fields in the area of printed electronics. So smart devices and IoT, energy storage and harvesting are also areas that have been growing, and there is a necessity that these areas grow because we are always thinking about more autonomous devices that can take advantage of the environment to create energy necessary to feed electronic devices. Batteries also bring a challenge to printed electronics, because usually when we think about printed electronics, we think about lightweight, high flexible. So if we don't have an harvesting unit that is also flexible, we lose a little bit of the purpose of the device itself. So energy storage is also being a very important topic in this field. printed displays, and also biomedical and healthcare applications that have been growing, and Centi has been involved in the developments within these areas. Here are some of the solutions that we can create with printed electronics, and as you can see, there is a very, very broad application field in terms of devices that can be generated through the combination of different inks, and it can go from different types of sensing solutions, from temperature, humidity, pressure. And please take in consideration here that we are applying in different scenarios. For example, this temperature sensor is an example that is applied on the construction sector to monitor the inner temperature of walls. The humidity sensor can be applied in different scenarios, but we are also having quite some nice collaborations with the construction industry to measure the humidity of spaces. Pressure sensors, here you have a pressure insole that can be used, for example, to monitor the posture or the movement of the user. Also different devices like heating systems, lighting, haptic feedback. So piezoelectric devices are also a type of devices that we can create to the application of printed electronics and generate smart functionalities that can go from vibration up to energy storage. So this makes a very, very interesting materials to work with. How can we think going from lab to industry with printed electronics? This is the main challenge that we address with our companies, and the way that printed electronics and other fields also must be addressed is define clearly these 4 stages in terms of technological development. So first of all, what is the main goal? And clearly, what is the problem that we want to solve with the company? How we can and how we will add value to the solution. Also do a very important market analysis and benchmarking, because in some cases we are thinking about a solution where we have already a commercial scenario that already solves the problem. So what is the intention to go and make an effort for it? And also something very important is defining the key KPIs and success metrics for the development, because we need to be able always to quantify the quality of the solutions that we are creating. Very important topic, and since we are multi-sectoral, this is always a very, very important stage for us, is to define clearly the requirements. So every application has specific technical specifications, specific regulations and certifications. You may imagine that what a printed sensor, for example, a temperature sensor that we want to apply in a vehicle in automotive sector, doesn't have the same regulations and certification than a temperature sensor that goes for clothing or for a wearable. So we are talking about completely different scenarios with different conditions to which the sensor will be applied, with different requirements in terms of durability, in terms of sensitivity. So all of these parameters are really, really important to define in an initial stage, because they will leave the base ground to which will make an impact in the type of technique that we explore for the development, in the type of inks and materials that we use, in the type of substrate, in the type of encapsulants that will be applied, and even in the integration process. So all of this is very important to define the approach. So when we go for the approach for the technological development itself, we must have all the requirements in consideration, and here we must consider the type of technological development that we want to address, the limitations that we have in terms of design, and how we can prototype and optimize the solution in the best way, taking into consideration which type of electrical tests, mechanical tests we will do, which type of materials will be applied. So all of this must be taken into consideration. And finally, but not less important, because it's one of the most critical scenarios, is integration. How? Because making a prototype, a TRL5 or TRL6 solution is one thing. Make a completely certified product that the company can insert in the market is completely different. So here we don't only develop the sensor, but we must think about the electronics. Do they comply with the certifications? How we are interconnecting? So one big issue that we have with printed and flexible electronic nowadays is interconnection. The connection between rigid, flexible in this case, to rigid, that are the electronics. So different types of connectors are being developed. Different types of interconnection techniques are also being explored. I'll show you some of them during the presentation. So all of this must be also taken into consideration. And at the same time, do all the testing and validation according to the requirements previously defined, and have a very, very, very careful selection about the process that we select in the approach, because it will have an impact in the pilot scale production line that we define further ahead. So if we want to go for screen printing, because the company will have a mass production of the devices, we must guarantee that this is the technique suitable to fill the requirements. So everything is interconnected, and we must take all of this into consideration from going to a lab to industry scale. Talking about a specific area, so in mold electronics, this is a domain of printed electronics where we integrate our printed devices directly in injected parts, and different types of process can be considered here with different levels of complexity. So in mold labeling is more focused on the integration of labels or tags during plastic molding. On the other hand, and in mold electronics, there is the area that I'll focus more, is focus on the integration of electronic circuitry directly in the part during its insertion in the mold and during the injection of the polymeric material. But also you can use printed electronics only as a decorative element. So instead of using, for example, conductive inks that you will use for in mold electronics, you can use decorative inks that will have color, texture, or aesthetic finishes to the final product, which is also really, really important and critical nowadays, for example, in areas like automotive sector, where we look nowadays at car interiors. We see really, really nice plastic parts with very good color finishing with this type of bright black. So all of this is achieved through this type of processes, and printed electronics has a huge impact in this type of solutions. Going to the more simple process, so in mold labeling, this is usually a 6-step process. So first of all, we print our solution with the decorative inks, or with, in this case, with the functional inks that bring out the tag or the label that will make a tracking of the part after its production. This label is printed on a flexible substrate that must be compatible with forming solutions. So because this is the second step, we'll give a specific form to our printed device. It will be cut in accordance in a form of label that is completely compatible with the mold where the label will be inserted in stage 4. And afterwards, we have the injection molding process, where we basically inject the specific polymer in the conditions where we can guarantee that both the temperature and pressure and requirements are being complied. And then we end up with our molded parts already with the label completely integrated. This is a similar process to mold electronics, but the difference and the requirements is much more different in the way that when we go for in mold electronics, we have an electronic circuitry. So we usually have electronic components that have volume, that have rigidity, that have a connection to the flexible substrate. For example, what you're seeing here on the left, it's an LED ribbon, printed one. So we have a printed substrate with conductive tracks and the assembly of LEDs on the top of it. This label has the format and is also cut in the format that it can fit to a specific cavity in the mold where it is attached. And then in the injection process, we have our resin or our polymer that is injected into the cavity. Issues: temperature, pressure, vacuum usually can be applied to secure the label. So we have a very, very harsh environment for the printed device. And this is the way that we must address during the fabrication of the label. We must address which type of adhesives are we using to attach the LEDs, which type of inks are being used, the design itself. Are we complying with the displacement with within the tracks, with the correct thickness of the tracks? Is the ink that we are using flexible enough to withstand the process? So all of these parameters must be addressed for in mold electronics to be succeeded. And we end up with, in this case, with the injected part with lighting completely embedded. In terms of decorative purposes, but not only decorative, because we can also have in mold electronics to these processes, and we have been contacted also already with some partners in this area. We can use in the left case, you have an example of in-mold decorative electronics, I would say, because we combine a printed circuitry that has buttons, as you can see on the right side. Do you see my mouse? Just as a question, I think so. But in case you don't, in the right side here, we have a matrix of buttons, but at the same time, this is a mask. This is a decorative mask. So we are providing both functions, both a decorative aspect, you'll see the part further ahead, but also a functionality aspect. This can be applied. There are different processes that can be applied in mold decorative areas. So we can also apply variotherm process where we are combining we are cooling the mold at a specific temperature to guarantee that after the injection molding, we have a much more smooth and bright surface. At the same time, there are already Portuguese companies that are working with 2K injection, where they basically it's an equipment. It's an equipment where we apply two processes at the same time. So it's a much more automatic process where we have the first step of applying the part and inject the mask. And in the second step, we have the backing of another injection part on the device. So it brings up much more complex plastic parts that are already being applied in the automotive sector. For example, in displays, almost every car nowadays has a display applied, and this is one of the ways to fabricate it. So in terms of materials, what must be considered in this area to have a success in mold electronics? Firstly, and one of the most important aspects is what is the polymeric substrate that we are using, because in mold electronics, we must guarantee that our printing substrate is compatible with the injection. It will be easily integrated during the process, so it must be completely compatible with the polymer matrix that is used. For example, if we are injecting a polyamide part, usually we will go for a polyamide substrate to guarantee that they have affinity. The thickness is really important because it affects the injection molding processes, the stretchability, and also, as I was mentioning previously, one of the most important domains, the mechanical and thermal resistance, because this is a very harsh process where the polymer it is at high temperatures and with a very strong flux that may have an impact in the label itself. In terms of functionality, the beautiful part of it is that we can use different types of functional inks or pastes that can go from highly conductive ones to carbon-based paste for heating circuitry, from functional inks, in this case, that are more for decorative aspects. And at the same time, difficulty assembly. So if you are thinking about in mold electronics, the part that I showed you previously, where we have printed tracks with the LEDs assembled, this assembly process is costly in terms of times, in terms of handmade. So there are not as much equipments right now that allow an automatic placement of these electronic components in printed circuitries. And this is clearly an area that will grow within the future to improve this assembly process. Okay. Nowadays, we know from the electronics field in terms of hardware that we have already flexible PCBs, so they are printed in Captain and they have copper tracks, but they are not as comparable to this type of printed electronics that I'm mentioning, because in terms of rigidity and flexibility, in terms of rigidity, they are much more rigid than these flexible solutions that I am explaining right here. But nevertheless, there are really nice advantages to go for in mold electronics, and that's why areas like automotive are adopting this type of solutions, because they bring out much more durable and high-strength parts, because we have a completely protected electronic embedded in the plastic part. We have a reduction in the number of production steps, because usually, if we think about automotive, the main harsh part is the assembly. So it's bringing all the parts together and guarantee that we can assemble everything together. And as much as more electronic components we have more time costs and more handwork within the device. which is not the most attractive way in a high cadence market like the automotive. We have a reduction in the weight of the final product. We have a minimal need for post-processing. If everything is completely validated, we have a completely reproducible process to be addressed. We can develop and incorporate technology directly into the production processes because we are using a process injection molding that is already completely used by most of the companies that are involved with composite parts. Different types of materials and finishes can be used. Mass production always leads to low unit costs, and we have a reduced waste and efficient material usage because we will need less material to be applied for the construction of these devices. Finally, some examples of how we can explore this type of solutions. In this case, I'm bringing you Vinci project. This is a project where here you can see the final prototype. So this is an automotive console that has here embedded different capacitive, haptic, and luminous feedback devices that are completely embedded in the part during its production. And namely the capacitive sensors and the sliders that you can see here are embedded during the injection molding process, allowing a final part with a very nice aspect. The same for Smart for Car. The Smart for Car is an example of printed capacitive sensors and a decorative mask, allowing the passage of light through the icons. This is a combination of two processes, so not only injection molding, but also thermoforming. Thermoforming is a process where we combine pressure and temperature to compact the layers to compact a multi-layer structure. In this case, what we had was multiple layers of our devices. Basically, just to give a brief explanation, we have multiple substrates. Within this layer of multiple substrates, we have one of the layers that has our decorative mask. We have other layers that has our printed capacitive buttons, and we combine and optimize these solutions to guarantee that we can comply with the design and with the functionality of all these buttons. Afterwards, this thermoform part can be also followed by an injection process area that gives this final finishing to the part. But when we think about electronics and print electronics in automotive, we can also think in other materials, like for example, foam, where we can print also directly in foam. In this case, this is a detection of presence or absence in a cup, something that we usually see also in vehicles. But so print electronics also bring this flexibility in terms of materials and applications that can be thought. As I was mentioning to you, automotive sector also is following the energy, because nowadays we see more and more investment in electrical vehicles, for example. So batteries are now one of the main components and main contributors of weight, for example, in vehicles, and a very growing area in the automotive sector. And the issue is that we need to have safety measurements for batteries, and this is something that we have already been collaborating with our industrial partners in the way that we are using printed electronics to monitor the life state of batteries. So usually batteries, when are becoming damaged or lowering their performance, they are having issues in terms of temperature, so hotspots, and these variations in temperatures can trigger defects, that can trigger fires, for example, that can compromise the safety of the vehicle for sure. All of us already heard news about car parts that burn totally due to a started ignition on an electrical vehicle. So this is the type of scenarios that we are talking about. And at the same time, usually a battery, when is becoming damaged, also can deform, can expand. So measuring pressure in battery is also an area where we have been making some developments, and one of the ways that we can apply printed electronics within this field. Another example that I wanted to show, you can see it, is a very nice project that ended 2 years ago. That is PAC. It was a mobilizer project focused on new concepts for for vehicles, and in this case, the shared vehicles in a city domain. So the idea here was how can we add technology to automotive interior through printed electronics, and here we have two different examples. On one side, we have here in number 2 a printed capacitive matrix for an interactive panel and image projection. So basically, imagine these are completely transparent printed electronics. So this is a translucent printed capacitive matrix that is laminated in the backing of a plastic part. So everything that is thought about in terms of light projection and retro projection was explored within the project. And in number 4, we have a solution of in-mold electronics, where we have a completely embedded display and also capacitive buttons to interact with a dial that is usually a component of the vehicles that controls different processes. When we think about automatic vehicles, so they usually have this dial to select the speed, to control the shift. So it controls different functionalities within the vehicle itself. Running out from automotive, but showing also you other examples of how we can apply printed electronics for different scenarios using in-mold electronics or using electronics integrated in composite parts. Here I shared you a concept of a project that was thermic, where we embedded heating systems directly during the thermoforming process of the insole of the shoe to have a completely integrated heating system on shoes. These are not standard shoes. These are shoes that are used as a PPE, so personal protective equipment for industrial people that works in very, very cold conditions. So usually they have the problem of having very, very cool extremities. So here, this type of thermal comfort can be added through printed electronics. And finally, one solution for homes, we have a solution that has a completely printed flexible PCB that is integrated to injection molding in a part that can be used in home to control different components. All of us see nowadays when we enter a space, specific displays to control the temperature, to control the humidity, to ventilate the room. So these are solutions where we can add a completely plastic part with all of these controls integrated, less weight, less components, much more easy to integrate. Making a shift to smart textiles, because smart textiles is also a domain that beneficiates a lot from printing technologies and from printing electronics, but the challenge is completely different. So when we think about in-mold electronics, we think about polymeric substrates, really, really thin, really, really flexible substrates that will be integrated in a mold and submitted to harsh temperatures. When we think about textiles, we have completely different structures. So we have fibers, we have yarns, we have porous structures that can absorb ink. So we have different conditions that must be thought about the substrate itself. So things like porosity, pilosity, stretchability, surface roughness. We know that textiles are highly conformable. We all wear them. So our shirts, our sweaters are highly conformable to the format of our body. So this type of solutions bring different challenge in terms of the area of printing electronics. That is why there are different approaches that we can imagine in this scenario. Things like direct printing onto textile is possible, but is one of the less applied processes in this field, because it only can be used in some specific textile substrates. Printing on an interface layer coated or laminated on the textile, which is something much more used within the textile field and the smart textile area. And finally, an add-on where we print on a polymeric substrate that is then laminated onto the final text. In terms of functionality, we can have different functionalities, from inks and pastes that can be used to improve the properties for different textile applications. And in terms of surface uniformity, because this is one of the main requirements, we can use membranes on one hand to be laminated on top of the textile, and then we can print our circuitry directly on top of it. But right now, there are also very, very different solutions in terms of ink and pastes that can be used as a first layer material to guarantee an uniformity in the surface of the text. So as I was mentioning, within the textile, smart textile area, there are different integration levels. So we can have add-ons. That is something that is most viewed in, for example, wearables. Sport athletes use these all the time, for example, to monitor their physical activity, GPS, things like that are already being add-on. And printing electronics is an area that is highly compatible with this. So we can have printed labels that can be laminated on the textile. Can be used, for example, in very, very broad biomonitoring solutions like EMG and ECG. We can have a wearable system, so we can directly print on the textile substrate and have it integrated onto the textile. And then we have processes that take advantage of yarns that are also areas where within Centi we have been collaborating. They are not focused on print electronics, but on flexible electronics. But it's also a very interesting topic to be applied for smart textile development. So taking a look of integrating onto. So when we go for this, these smart features can be produced by printing or coating directly onto the textile substrate. Different types of strategies may be employed to reduce the surface roughness and promote the surface quality. And usually the main process that is used is screen printing directly onto the textile. This process can be direct, as I was mentioning, so we print directly on the textile substrate, or can be indirect, so we print firstly an interface layer. A specific case study that I would like to share with you is a textile patch for high-density EMG monitoring. So EMG is a process where we cap the electrical signal from muscles. I think from the previous presentation you already saw this type of solution. Basically, what we are doing here is high-density EMG, so we are bringing up much more electrodes on this scenario, and we can capture a much more a specific electrical signal in terms of muscular contraction that can give us some indicators about the muscular performance of the user. In terms of this device development, it was developed in a knitted textile structure. So knitted are much more lightweight in many cases, much more flexible. We needed to uniformize the surface of this knitted. And basically, the main difficulties that we had was our printing process is very sensitive to the textile characteristics. The performance of this interface layer, because needles are highly stretchable, highly flexible, and we had to make a very profound study of this interface layer, because in many conditions we have a breakage of our threads due to the fact that our surface layer was not uniform, and it's also impacted a lot the mechanical properties of the textile. So this interface layer is very important to study and to test different materials, because one thing is to have a uniform surface, but if this uniform surface compromises the mechanical properties and the functional property of the textile itself, we are already committing some errors in the development that we are making. And finally, we have the add-on integration, which is much more versatile in the way that we can print on separate substrates and laminate. We can have electronic add-ons that can be applied. It's very compatible with the different types of commercial devices. Also, we can put directly commercial devices on the structure and use, for example, print electronics to make some interconnections. So this is a much more less demanding process in terms of integration, and it's more dedicated to confection of the textile itself. A case study that I bring you is for example, pressure sensors that can be prepared in a completely controlled environment in labs. So we can develop the structure of our pressure sensor. In this case, this is a strain gauge, piezoresistive, so 3 layers, electrode, sensitive material to pressure, and another electrodes. And we produce the device, we laminate it we use a specific substrate that can be laminated further ahead to a textile. We encapsulate the device, so we have a completely off-the-shelf device that can be laminated in different types of textile structures. And like this, we can have a much more simpler device to integrate. In many cases, the difficulty that we can have is the limitation of the textile, because some textiles may not have a good adhesion for the adhesive that we use. and in some cases, depending on the textile, it can affect also its mechanical properties. As I was mentioning in mold electronics, also in smart textiles, the challenge is interconnections. So how we can make this bridge between rigid to flexible. There are different scenarios used nowadays for hybrid solutions and interconnections that can go from snaps, which is the most used one in terms of e-textiles, I would say, because it's something already very, very close to what the textile industry uses. Most of our pants have this type of snaps embedded. So it's very, very close to a typical confection processes. But are other structures that can be used like soldering, conductive adhesives, conductive structures, electrical connectors, standard connectors that can be applied for printed circuitries, for example. So some FPC connectors that are already available in the market. But all of these solutions have a problem that is they are customized. So nowadays we don't have a standard process that can be used for interconnection and that can be applied in all of the scenarios. And nevertheless, there are already some interesting companies and players working in this industrialization of textiles through automatic processes that allow the integration of electronics. And one of them is Free Smart Solution that developed customized embroidery processes that allows us the integration of LEDs and flexible PCBs directly onto textile-based substrate. This is an equipment that we have here at Centi, and we invite you all to visit us if you want to have access to it. But at the same time, this equipment is also very interesting for the print electronic field because it can be combined with the embroidery process. So we can use embroidery as an interconnection process for print electronic circuitries on textiles. So this has a high potential of industrialization for print electronic devices. At the same time, we have other companies like, for example, Fraunhofer, that has developed a customized molding process that is already very close to a market application. Finally, just to share with you some solutions, there are different areas where e-textiles with printed electronics can be embedded, from monitoring solutions like biomonitoring, ECG, EEG, sweat, breathing rates, from temperature, humidity, gas detection. These are some of the solutions where printed electronics and e-textiles can be used. Something very interesting also is structural health monitoring, because we have been having some collaboration with the construction, composites, aeronautics, automotive that want to know the quality of their parts and the structural integrity of their parts, because usually they are submitted to high demanding parameters, so monitoring bending, vibration, the detection of water. In many cases, water will lead to damage on the structures. So these are areas where e-textiles that act as textile reinforcements will have a role, and a very interesting role in the future. Lighting solutions, and here we can use different types of devices, from printed electronics up to bulk devices that have printed electronics as an interconnection. So here we are thinking about LEDs, optical fibers, LED matrixing, up to OLEDs. So different devices can be applied. And here I have an example of a rug with this type of embedded technologies. This is a solution for automotive interior also with different types of lighting applications. So here we had the integration directly of LED tracks, optical fibers, and electroluminescent devices directly in car parts, in this case in the door panels. And we created different door panels for the vehicle. And it was a project with a Portuguese company, namely Simoldes, where we developed quite some interesting solutions. So this was a little bit of what I wanted to share with you. So the main conclusion here is that, in fact, printed electronics have a huge potential of application, and we have different areas where we can explore it. And once again, in case you have any questions, any doubts, please don't hesitate to ask. Thank you.
Thank you so much, Kevin. Amazing talk also. Thank you so much. And I think you raised really interesting aspects, not only on the printing part, on the different devices that we can tackle, but also very important on the integration challenges. I think that integration is really a key part of this topic, both for the more, let's say, conventional flexible and electronics, and also for textile electronics. So for people wanting to address questions, I know that before the raise hand was not working. You can either raise hand or you can write here in the chat. So we have one question here. What are the typical inks used in smart textiles made of?
Okay, it really depends on the functionality, but usually for example, I'll give you some examples because it's much more easy to apply. But silver conductive inks are widely used on e-textiles. Everything that is connected, for example, to biomonitoring, usually is based on electrodes. So in electrodes for ECG, EMG, we are always thinking about high conductivity. And in this case, there are already some nice commercially available inks in the market to allow this. Main requirement, flexibility. Okay, this is one of the main requirements for that. But in fact, there are not so many limitations in terms of conductive inks that can be applied. In many scenarios, we can use carbon-based conductive inks for piezo-resistive approaches, for example. So it's a way to adapt the materials to the device that we want to build up. At Centi, for example, we'll also explore the development of our own conductive or functional inks, because in many cases, for example, we are working with biosensors, so we need to have a specific membrane that is selective to a specific analyte, like glucose, for example. So here is a combination of materials, and you use silver for the electrode and use our functional inks for the membrane. So it's a way of combining. So I think that is not a right answer. That is not a specific ink that can be used. It really depends on the scenario.
Yes, exactly. Any further questions from the audience? I would ask one question, Kevin. So you mentioned pretty important thing about these bonding processes, particularly for textiles. So can you elaborate a bit on how customized these things need to be? I think you presented an example from a Fraunhofer Institute mentioning that they have a sort of customized. So of course, without entering into too much details, of course, but what exactly needs to be changed compared with the solutions that we already see popping up in the market of flexible electronics here?
Yeah, the issue that we have with flexible electronics, namely for e-textiles, because e-textiles, it's a model of our neighbors, but textiles are everywhere. So really, textiles can be applied with a multi-sectoral approach. In the textile industry, it's a sector, but it's a sector that feeds almost all the sectors around it. And in Portugal, we see it clearly because we are mainly, as in the north part of Portugal, we have really, really strong industries that work for different areas. And having a specific interconnection process that fits all the solutions usually is not possible, because usually they have much more different requirements. It's very different to bring up a sweater with an embedded temperature sensor that will be submitted to not standard, but environmental parameters. So we will use it in a normal temperature environment. Then bringing a textile that will go for a composite reinforcement structure that will be submitted to really, really strong temperatures, high mechanical demands. So here the interconnection process is really, really important. I mentioned out these two solutions because from what we have been detecting and also exploring, of course, this customized bonding process from Fraunhofer is a proprietary technology. From Centi, we don't have access to it, but it's something that from the state of the art that we can see is one of the solutions that is really, really close to the market. And it's a very, very reliable tool to make the fixation of electronics directly into textiles. At the same time, these three smart solutions is also an area is also a very, very interesting solution. In this case, we have this technology indoors, and we are clearly seeing that it brings up much more reliability in terms of the integration of electronics in textiles. But I would say that the customization of the interconnection right now is a necessity, because right now we need to have a customized interconnection because we have specific number of sensors, specific characteristics of the devices, specific yarns that must be used, or specific inks. So there's always some customization. Something that must be developed, and these are the first steps, in my opinion, is automatic processes to address this customization. Because these processes are customized, but they are customized in the way that you can scale up afterwards. And this makes a huge difference.
Yeah, definitely. Thank you. So any other question? A last opportunity for questions. There's one here in the chat. So at laboratory level, it's difficult to avoid impurities. So at an industrial level, how to get pure materials for sensors?
That's a really nice question, and that is why when I make that slide of requirements and approach, and everything must take into consideration in that aspect. Because in some cases, if the industrial scenario for the production of the devices, you cannot have a controlled environment, you must change the materials in the initial stage. So I would say that if you cannot avoid it, change it, because otherwise you will get hurt in the final stage. And this is why it is very, very important to have a very first profound evaluation of the development that you will do. Because in many cases, you are making a development of 1 year for the company, and you're using a material that at a lab scale, it works always. But then you go to the company, you try to reproduce the solution, and it doesn't work. So it's very, very important to have a specific know-how of the requirements and characteristics of the process of our partners to adjust the solutions accordingly. Okay, if you go, for example, for our roll-to-roll machine that works with the conductive inks, we don't have this issue in terms of material contamination, because we can put there 1, 2, 3 kilos of ink and it stays in a controlled environment. So the equipment guarantees itself. But if you want to use the screen printing process of the company and you cannot guarantee this pure level of the ink, you must adjust it. So this is the most correct approach to be made, because usually companies, if you develop a solution that you know for sure that you validated in an industrial scale and the company can explore it, this is one way. If you develop at a lab scale, but you say to the company, okay, if you want to do it, you need to make an investment of millions and millions to address this. This is another completely different topic. So this is one of the challenges that is required from lab to industrial scale to be addressed.
Okay, Kevin, thank you so much for participating in the school with your contribution. Thank you so much.